We're going to continue our discussion of bonding by discussing covalent bonds and electronegativity. So as a review, a covalent bond is something that forms between two nonmetals. So for example, two atoms of oxygen, two atoms of hydrogen, and one of oxygen. And nonmetals, remember, they have a high ionization energy, which means it's really difficult to remove electrons. And since neither one readily loses electrons, what they do is they share them. And so the idea is that you have this nucleus, and then you have this area where their electrons are shared by both nuclei. And this would be our electron orbital. We'll talk more about orbitals later, but for now, all you need to know are that orbitals are where you're going to find these shared electrons. So let's use the Lewis theory to examine covalent bonds. We'll use chlorine as an example. So here you see our two chlorines, and we know that they have 7 valence electrons. So if we distribute these valence electrons evenly around both of our chlorine atoms, we see that we have 1 unpaired electron. So when these two when these two atoms come together to form a molecule of diatomic chlorine, what happens is this bond is made up of 1 electron from this one and 1 electron from this one. So now we have each chlorine seems like it has 8. So this nucleus can see 8 valence electrons, and this nucleus can see 8 valence electrons. So in this way, an octet is achieved even though there was no actual transfer of electrons. So we'll show this with arrows, where we have our arrows moving to push our electron towards our bond. And we can see that we started with our configuration of 3s2, 3p5, and now they each have the argon configuration, which means that we have the noble gas configuration. So again, we didn't create a noble gas, we just gave these chlorine atoms the noble gas configuration of electrons to satisfy the octet rule. Let's practice by predicting the structure of H2O. So with H, each of them have only 1 valence electron. Oxygen has 6. So this electron can form a bond here from this hydrogen and this oxygen, and this electron will form a bond here between this hydrogen and the same oxygen molecule, showing that the hydrogens each have 2 and the oxygens have 8. So we called it the octet rule, but since hydrogen is so tiny, it only needs 2 to fill its outer valence shell, right? Because the valence shell is the 1s orbital, and there's only 2 electrons that fit there. Helium also only has 2 electrons in its noble gas configuration because, again, it only has a 1s orbital, and that 1s orbital only holds 2 electrons. So let's use our little arrows. We push our electron here and this one here to form a bond. And this electron gets pushed here and this here to form a bond. So now we have our octet and our duets. And these here are called bonding pairs, and these are called lone pairs. So let's predict the Lewis structure of oxygen. So here we have our 2 oxygen atoms. They have 6 valence electrons, so they have 2 unpaired electrons. So we see that they have our 2 lone pairs, and then we can move these electrons to form a bond here and then here. So now we get a double bond. So here we have our octet, 1, 2, 3, 4, 5, 6, 7, 8 for this guy, and then 1, 2, 3, 4, 5, 6, 7, 8 for this guy. So we have a double bond between these 2 oxygen atoms, and 2 lone pairs on each oxygen atom. Let's predict the Lewis structure of N2. So let's look at our periodic table. We see that N is in this column, so that means it has 5 valence electrons. And what happens is we need to have a triple bond between the 2 ends because they'll have 3 bonding pairs. So let's think about this. When we have a single bond, generally the bond strength is lower and the bond length is longer. As the bond length decreases, the bond strength increases. Now this makes sense. Remember Coulomb's law that as 2 charged species get closer to each other, that the attraction is greater. So our nitrogen here started with 5, and this guy started with 5. So they had, each one had a lone pair and then 3 single electrons for bonding. So you can imagine that 1, 2, 3 came from this nitrogen, and 1, 2, 3 came from this nitrogen, and now we have a triple bond here. So this triple bonded nitrogen is going to have a very strong triple bond there. So melting points and boiling points of these compounds are lower than ionic bonds because they have weaker intermolecular forces. So Coulomb's law is really, really strong for ion attractions because we have a full positive and a full negative charge. But with a covalently bound molecule, what's happening is you have this one molecule. There are covalent bonds in here. This molecule can interact with other molecules around it, but they don't interact nearly as strongly as two charges, so a positive and a negative charge. When you are boiling something, what you are disrupting is the intermolecular forces or the attractions between molecules. You are not breaking covalent bonds. You can remember this because when you boil water, steam is gaseous water. Steam is not hydrogen and oxygen gas. If that were true, you would probably blow yourself up with your gas stove. Okay? You are not producing oxygen gas on your gas stove when you boil water. What you're producing is water vapor or gaseous water molecules. But you had to break the interactions between liquid water molecules. So in this example here, they're disrupting the weak intermolecular forces between pentane molecules here. The covalent bonds are very strong. They are within molecules. The weaker intermolecular forces are between molecules. So there are some limitations of this Lewis model. Here's an example. What is the Lewis structure for HF? So the Lewis model does not tell us when there's unequal sharing of electrons. So what do I mean by this? Well, fluorine is really electronegative, which means it attracts electrons to itself in a bond. Hydrogen doesn't really pull electrons towards itself, and so it tends to have a somewhat partial positive charge on the hydrogen. So you can kind of think of this as like a party. The electrons spend most of their time in one room of the house party, not the other rooms. This fluorine is the life of the party. The electrons spend more time by the fluorine. This is the introvert that doesn't really want to be there. The electrons don't really spend much time over here. So the electrons, even though it's a covalent bond, they are being shared. They're in the same party, but the electrons spend more of their time over here. This is what we call a polar covalent bond. It's polar because it has a pole. It has a positive end and a negative end. And this is MAP, called an electrostatic potential map that shows the positive in like the bluish colors and the negatives in the reddish colors. So electronegativity is the ability of an atom to attract electrons to itself in a chemical bond. Remember, this is not the same thing as electron affinity. It's very similar. It follows, you might notice, the same trend that electron affinity follows, but it is not the same thing because electronegativity is only concerned when it is in a covalent bond. So how well does the atom, when it is covalently bound to something else, how well does that atom pull the electrons towards its side of the covalent bond? So, why is electronegativity proportional to the inverse of atomic size? We see that electronegativity increases in this direction and atom size increases in this direction. Well, larger atoms are less likely to attract electrons to their nuclei because the nuclei are shielded by these outer electrons, and so there's less of a pull that the nucleus can exert on those on those valence electrons. So here is a kind of a summary of the effect of electronegativity differences on bond types. So when you have a diatomic covalent bond like chlorine, molecular chlorine, or molecular nitrogen or oxygen, since the atoms are the same, they have exactly the same electronegativity, there's no difference in charge attraction. That would be a pure covalent bond. If there's a small electronegativity difference, then you have this, what we call an intermediate difference, where you have this partial positive and partial negative charge. This lowercase delta is what we use to indicate a partial charge. So this partial positive hydrogen and the partial negative chloride, it's still a covalent bond. There's still sharing of electrons, but the chloride pulls most of the electrons towards itself in this covalent bond. So there's uneven sharing, which gives it that pull. Last but not least, we have these large electronegativity differences which lead to these ionic interactions. So for example, sodium and chloride, where you have a full positive sodium and a full negative chloride. So you'll notice that for our polar covalent bonds, we have partial positive and negative charges, and for our ionic bonds, they're full positive and negative charges. So here's a little cartoon that might help you understand this a little bit better. You could think of it as tug of war when you have a large electronegativity difference. Atom A doesn't pull as hard on the electrons as atom B, so the electrons are further towards atom B. When an ionic bond happens, there is no tug of war anymore. This guy won, and so the electrons are in this atom's orbitals, not here. So this is a positively charged ion, and this would be a negatively charged ion, and they could interact with each other. Oops. So you do not need to memorize this information here. This is just a general rule. What I would like you to be aware of is the differences between these bond types and be able to use the right symbols to demonstrate a polar covalent bond and an ionic bond. And then if you were given electronegativity differences, if you could predict which it would be, a covalent, a polar covalent, or an ionic bond. So let's do some practice. Let's classify the bond formed between each pair of these atoms. So, strontium and francium. So we have to find this on our periodic table, and I think it's actually not showing up here. So, but these are our molecules here. Oh, I'm sorry, it is here. So strontium and okay. So let's do some practice. Let's classify the bond formed between each pair of these atoms. So for A here, we have strontium and fluorine. And so we see that strontium is a 1 and fluorine is a 4. 4 minus 1 is 3. So it's probably ionic. The other hint we have that this is ionic is that this is a metal and this is a nonmetal. N and Cl. Here's nitrogen at 3 and chlorine at 3. They have the same value, therefore we would call this a pure covalent bond. So this is not a polar covalent bond, it's just a covalent bond with equal sharing of electrons. N and O. Nitrogen has 3, oxygen has 3.5. The difference is 0.5. So it's barely polar covalent. So oxygen is going to pull the electrons towards itself in its covalent bond with nitrogen. So this would have the delta minus, and this would have the delta plus. This arrow is something that we use to show the dipole, the direction. It is a vector, which means that it has magnitude as well as direction. So it's important that you pay attention to the directionality of this arrow, because if there are two arrows that are in exactly opposite directions, they will cancel out. So here's our summary for covalent compounds. When we use Lewis symbols, we can show how two nonmetals share electrons. A sharing of 2 electrons is a single covalent bond. Sharing 4 electrons is a double covalent bond, and sharing 6 electrons is a triple covalent bond. The melting and boiling points tend to be lower for covalent compounds than they do for ionic compounds. The Lewis model does a poor job at representing polar covalent bonds. In order to do this, you will need to examine the electronegativity of the atoms to see which one pulls the electrons closer to itself, and when that happens, you will use a dipole arrow to represent the polar covalent bonds and use the delta plus, delta minus to indicate the partial charges.